We are Group 5 and we are covering COVID deaths across different countries, looking specifically at the country's different demographics. Some background on COVID-19 is that the first symptoms popped up in December 2019, aging the pandemic to around 2 years. The first vaccine became available 11 months ago, and it has been proven that certain conditions can cause COVID symptoms to be more serious, for example, diabetes. Other things that have been shown to cause higher COVID cases is lower income environments as well as older age. Further details about COVID-19 can be found here. Being that we researched COVID-19 deaths across different countries, here is an overview from CNN Health of deaths per 100,000. The darker the green, the more the deaths. This data was updated on November 21st of 2021 with total deaths of 5,150,303. More specific background on our group's research is that we looked at data from Our World data that included all countries, but from there we chose to look at the top 150 countries with the highest vaccination rates found from CNN Health, which was also based on Our World Health. Then we chose 50 countries from those 150 based on available data, country size, along with some other factors. For example, though Gibraltar had the highest vaccination rate, we chose to delete it due to no available data on death rate. We also got rid of the Pitcairn Islands due to the extremely small population and along with total vaccine dosages of only 94. Here is a list of the 50 countries we chose to research, including bigger countries like Canada and Australia, but giving variation with some smaller countries like Zimbabwe. Our general research question is, are there any explanatory variables relating to the demographics or COVID-19 response of a country that can help explain death totals? Our explanatory variables are listed as vaccination rate, age of population, GDP per capita, population density, diabetes prevalence, and case rate with a response variable of deaths per million people in the last 6 months. Our null hypothesis is that the country's demographics have no effect on deaths per million numbers, and our alternative hypothesis is that any of these countries' demographics have any effect on the deaths per million numbers.
So for model diagnostics that we ran on the test variables, here's the summary table of the full formula and the ANOVA type 1 and type 2 tables. From the full model summary table, the case rate was the only, the case rate was the only variable that showed a significant p-value. In the type 1 ANOVA table, vaccination did as well, but in the type 2 ANOVA table, case rate was the only one that did. So it's the only one that showed significance in all three tables. So we ran a scatter plot to show, to test whether there was multicollinearity, and we see that there's some possible multicollinearity between vaccination and age, 65, which would make sense since it was rolled out in an age order fashion, and possible between vaccination and GDP as well. So then we did a normality and variance, constant variance tests on it. So you can see from the plot of the variance that there's not constant variance. There's a lot of plots kind of close and below, and then a lot that are very high. So it's not really equal. And then as far as normality goes, the Shapiro-Wilks test clearly shows that there's normality violations, as does the QQ plot. So then from there, we want to look at outliers and influential points. So when we did the studentized deleted residuals test to determine Y outliers, we had only one show up. That's number 26 there. But the value had to be greater than 3.5, and the value of it was 3.9. So we kind of determined that that was close enough to where we weren't going to make any changes of that one. We just left it in there. And then when we did the test for X outliers, the uh, the value of H bar had to be 0.28 to show outliers. And you can see that there's 5 of them here, but 4 of them are pretty close to 0.28, so we left them alone. But number 5 here is 0.96, so we thought that would deserve another look because it's pretty far away from 0.28. And then if you look at this graph down here for population density, there's number 5 right there. That's the reason it was an outlier because its population density is very high. And it happens to be Singapore, so its population density was 15 times higher than any other country, the next highest country. So we ran a Cook's distance test on the data, and as you can see here, again, in the red square or rectangle, um, it showed as being a heavily influential point due to that population density. So we decided to remove it from the data. And after we removed it from the data, we ran the Cook's distance test again, and we did not have any influential points from there.
As Nate mentioned, after the removal of Singapore from the dataset, we no longer have any significant influential points. This is further evidenced by a scatter plot of the new dataset. As you can see, these plots, especially the ones corresponding to population density, have improved significantly. However, despite the improvement, a transformation of y is still necessary as the residuals fail the assumption of normality and constant variance. So, here's our plot and lambda value used to transform y using the Box-Cox transformation. This transformation leads to significant improvement in the residuals. As you can see, the QQ plot is looking much better. There are a couple of possible outliers, but based on our earlier Cook's test, none are significant enough to eliminate. A Shapiro test shows a p-value above 0.05 and thus concludes the residuals are normally distributed. We also ran a Brown-Forsyth test for each variable. This slide shows just one example, the examples of case rate, but all other variables had a high p-value as well, leading us to conclude that the transform residuals have a constant variance. From here, we can analyze our summary and ANOVA tables of the transform data. We conclude that vaccination rate, GDP, population density, and case rate all have significant linear impact on Y, or deaths per million. This is a major change from the original model, which only showed case rate as a significant predictor. We also note that while diabetes does not have a p-value below 0.05, it's not far off at 0.05968. Using the transform data, we use a forward step function to determine our best model is one which consists of vaccination rate, GDP, population density, diabetes, and case rate. We found no violations of normality or constant variance using the model. We also found the VIF of the model to be 2.108312. Considering this is well below 10, we concluded there is no significant multicollinearity. To test our model, we ran a 10-fold cross-validation and found our model had an RMSE of 0.91, which was an improvement over the model containing all the predictors, or the full model, which had an RMSE of 0.86. As a result, we're able to reject our original null hypothesis and conclude that there are country demographics that can be used to describe COVID-19 deaths. Specifically, we found vaccination rate, GDP per capita, population density, diabetes prevalence, and case rate all had significant linear impact. While this model provides a start towards determining the factors that affect COVID deaths, there are some limitations. The first of which is a relative lack of data. Compared to other viruses, COVID has had a short-lived life, and more data will be needed to come up with the most accurate predictions. Lastly, we wanted to attack data from all over the world because COVID is a global issue, but the relationships between predictors and deaths may be clearer using local data. If we were to go further with this study, we would choose the data of a few countries for which multiple cities collected data. This analysis at a state level paired with our global analysis would strengthen the results we saw in this study. That concludes our presentation. Thank you.